to you have to design it. The final design you have to construct it. The final design of Chekhov's learning system can be described by four distinct program models that represent the central components in any learning system. You have to use the design for the what do you call it as Chekhov's algorithm. The first one is experiment generator, right? So and you have the new problem, the initial game board, the performance system, and solution trace just by using the history. And if there is any problem with the system, so what you can do is that you just update the values of the training values, right? Generalizer. Then finally what you do is that you just hypothesis in the sense you're just changing the what you call it as the error rate. You just try to change the weight in such a way that you are going to reduce the errors. Once it is done, you are just again applying the rule for the experiment to check whether it is going to meet the performance. And if it is not going to meet the performance, then again you're changing the training examples. Once it is going to be changed, once it is changing the training examples, again you are changing the errors weights, so that you will get the ultimate you get the final the performance. So this is what the final design for the checkers playing. The final design of checkers learning system can be described by four distinct program models that represent the central components in many learning systems. The first one, the performance system, is a model that must solve the given performance task by using the learn target function. That is, this is the module that is going to solve the learn target function. It takes an instance of a new problem as input and produces a trace of its solution as output. In checkers game, the strategy used by the performance system is to select its next move at each step is determined by the learn uh, learned evaluation function. Therefore, we expect its performance to improve as this evaluation function becomes increasingly accurate. Okay, so this performance system will generate the output for a given input, or it's going to generate an trace for a given input. That's why it is going to see whether it is going to meet the performance criteria or not. If it is doesn't, if doesn't meet the criteria, then what it will do is that it will go back and change the weights. And the next stage in the design is that the critic takes an input of history of the game and produces as output a set of training examples of the target function. As shown in the diagram, each training examples in this case corresponds to some game state in the space, along with an estimated weight training of the target function value for this example. So if you are not meeting the performance criteria, then you are the critic function or the critic stage will it's going to generate the set of training examples. It produces the set of training examples of the target function. And the next one is a generalizer. Takes as input the training examples. Whatever the training examples you have generated in the critic stage, it will take that as a input and produces an output that hypothesis, output hypothesis, that is that it estimates the target function. It's going to estimate the target function. It generalizes from the specific training examples, hypothesizing a general function that covers these examples and other cases beyond the training examples. These output hypothesis is going to generalize the function, and also other cases that is beyond the training examples. In our example, the generalizer corresponds to the LMS algorithm, and the output hypothesis function we have, which is described by the for learned weights, that is W0 to W6. The generalizer is going to generate the hypothesis that is from the given training examples. The experiment generator takes as input the current hypothesis and outputs a new problem, that is a new initial board state for the performance system to explore. Its role is to pick new practice problems that will maximize the learning rate of the overall system. It will the main role of the experiment generator is to produce the is to maximize the learning rate of the overall system. In our example, the experiment generator always proposes the same initial game goal to begin with a new game. So that is what. So the all in all, the final design states it's going to experiment, or it's going to change the states in such a way that you are going to meet the criteria. You are going to meet the final states. These are the sequence of design choices made for the checkers program is summarized here. Determine the type of training experience. Okay, you can decide whether you are going to get the training experience. Again, some more. You can either play with the experts, or you can play against yourself, or you can play against table of correct moves, or some other way you can get it. So these are the training experiences you can get it. That is, you can play against an expert, or against itself, or the self, or you have a table of moves. You have to play against that, and other means of getting the experience. And if you're playing against itself, determine which what you call it as the target function you have it. Sorry, determine the kind of the target function. Once you have set the target function, determine the learn representation, how the representation will be done for the learn function. Either you can represent using polynomial move, sorry, polynomial, or you can use the linear expression function of six features and artificial neural network. Using any of these, you can represent the linear function. In case of the linear function of six features, you can determine the learning algorithm, whether you are using gradient descent or linear programming or other algorithms you are using it. Once it is done, your design is complete. So this is how your checker algorithms or learning algorithm works actually. So you have to decide whether in the first level, you have to decide whether you want to play against an expert, or you want to play self, or you want to play against a table of correct moves, or anything else. And once you decide it, you have to determine the target function. That is, you have to determine the move, or you can determine the board value. So in case of the board value, determine the kind of the representation for the learned function, whether you want to represent using polynomial values, or you want to represent using linear function, or you want to use the artificial neural network. In case of the linear function, determine the learning algorithm, what kind of algorithm you are using it, gradient descent or linear programming or any such algorithms you are using it, and complete your design. That is what the complete design of uh, the checkers learning algorithm. Similarly, you can do with the other problems as well. And there are some issues with the machine learning. So let us look at what are those issues with the machine learning. What algorithms exist for learning general target function for specific training examples? That is, you don't know what is there any algorithms exist for learning general target function from the specific training examples. You don't have an idea of that. In what settings will particular algorithms coverage to the desired function given sufficient training data, and which algorithms perform better for which types of problems under the representation. These are some issues. That is, the first question that has to be asked: is there any algorithm that is going to uh, exist for learning general target functions? And if at all you have the general target function, and what settings will particular algorithm coverage, and coverage to the desired function given the sufficient training data, and among all the available algorithms, which one is going to perform better? Okay, that is one issue with respect to machine learning. And the second one is that how much training data is sufficient. If at all you have good target function, but how much data is sufficient? How much data you are supposed to pass for the given the training example? What general bonds can be found to relate the confidence of learned hypothesis to the amount of training experience and the character of the learner's hypothesis base? So you have to decide what kind of data you are using it, and what is the level of the confidence of learned hypothesis as well, and when and how can prior knowledge held by the learner guide the process of generalizing from examples. So whether the prior knowledge of the learner will help in generalizing from the examples or not. Can prior knowledge be helpful even when it is only approximately correct? Even though if you have some knowledge, prior knowledge, but uh, that is not correct or that is not full, but whether it is going to help you and build the solution or not, that is these are the some things, some issues with respect to machine learning. That is with regard to uh, the learning target functions, with regard to training data, with regard to the knowledge of the learner. Okay, with regard to general target function, whether you have a sufficient large is there in exist a particular target function or not. If at all there is a target function exist, whether is it going to accept all kind of data or any kind of data. If there are multiple target functions you have to assess the performance of each one of them to select the best out of them. And the second one is what how much data is sufficient for what you call as for the target function. Okay, and the third one, the prior knowledge of the learners is very important. Whether having a little prior knowledge will help in building the solution or not. And what is the best strategy for choosing a useful next training experience? What strategy you are using to get the new training experience, and how does this choice of this strategy alter the complexity of the learning algorithm? And what strategy you are going to choosing a what strategy you are using for choosing a useful next training experience, and how does the choice of this strategy alter the complexity of the learning problem? If you choose a strategy, how this is going to alter the complexity of the learning problem? What is the best way to reduce the learning task to one or more function approximation problem? That is how we are going to reduce the learning task to one or more function approximation problem. Put another way, what specific function should the system attempt to learn? Can this process itself be automated or not? That is how to reduce the learning task to one or more approximation function or the approximation problems. And uh, what specific function we supposed to learn it, and how can the learner automatically alter its representation to its improve its ability to represent and learn the target function. How can the learner automatically alter its representation to improve its ability to represent and learn the target function? How much the learner can automatically alter the representation? These are the some issues with respect to the machine learning, with regard to the algorithm, with regard to the what you call it as the training data, with regard to the learner's ability, and with regard to what you call it as the task, or the with regard to the training experience, and with regard to the representation. Here we are talked about training experience. We have seen it, how to take the training or the choosing the how to choose the training experience, and the target function and representation for the target function, right? And function approximation algorithms we have seen it, that is estimating training values as well as the adjusting the weights, how to adjust the weights. Based on that, we will get the uh, good approximation algorithm. And finally, once everything is over, you have to design the final system. So that is what we have seen it. This is all about the learning system design process, right? And this is what we have seen it. We are assigning the value for each one of them, right? So the weight for each one of them, W naught, W1 up to W6. These are the weights, and X1, X2, X3, X4, X5, and X6 or nothing but the values or the instances what you are considering it, right? And we want to achieve the approximations in such a way that by just altering the values of w's or the weights, we can approximate the entire function to the things. So for that reason, you are just changing the values of the weights, that is w0 to w6. So this is the one more things here, that is what is the target function representation you have it, right? And how to choose the things here, that is how choosing a perfect approximation algorithm, that is what I am doing is that you're just setting the values. We're just looking at whether this one is whether you are choosing the particular training example or not. If you're choosing the particular training example, it will be considered as one, otherwise it will be set to zero, right? And approximation procedure, we have seen it. So we are estimating the training value for the its successor, right, based on the training value of the current instances, right? And this is all about once everything is over, we are designing the final set, right? This is what the things we have it: the performance system, and experiment generator, then followed by the performance system, the critic, and followed by the generalizer. Okay. And this is what the sequence of the design choices you have made it. So they determine the type of training examples. Either you can have the games against the exports, games against the self, and table of correct moves, or something else. And within the games against itself, determine the target function, whether you want to have the board or board value. So okay, so for the board move, again you choose determine representation of the learn function, whether it is a polynomial, linear function of six features, or the artificial neural network. And finally, it is the determine the learning algorithm for the linear function of six features. And you have the gradient descent, linear programming, and finally this one. So this is how we can make the choices or the design choices based on your experiments or based on your choice. And there are some issues we have seen it, that is a machine learning algorithm. In the machine learning, there are some issues we have discussed it, that is what algorithm exists for learning general target function from the specific learning or the training examples. Is there any exist algorithms that we don't know it? Okay, so we have to build the algorithms on our own, or if at all there are some particular algorithms, you have to make use of that. And if there are many multiple algorithms are available, you have to make a choice of a particular algorithm based on their performance and how much training data is sufficient, right? This is one more important issue of the machine learning: how much training data is sufficient, that is whether you want what quantity of the training data is sufficient to evaluate the system. What general bonds can be found to relate the confidence in learned hypothesis to the amount of training examples? And when and how can prior knowledge held by the learner guide the process of generalizing the examples? That is how the prior knowledge it helps in building the system. And also, what is the best strategy for choosing the useful next training example? So what is the best example for choosing the best training examples or the training experience? What is the best way to reduce learning tasks to one or more function approximation problems? And finally, it is how can the learner automatically alter its representation to improve its ability to represent and learn the target functions? And the next concept we are talking about is the concept learning. Okay, and the concept learning involves acquiring general concepts from specific training examples. For example, people continually learn general concept or categories such as bird, car, situations in which I should study more in order to pass the exam, etc. That is, there are some concepts, right? They are learning some the things from a general concepts, right? That is, for example, birds, car, and so on, right? And in case of the birds, right? Birds, there are all specific training examples, right? And these specific training examples are we are learning it from, we are learning, and this process we call it as the concept learning, right? Even with the respect to the car, so this is a specific training example of four wheelers, right? It's a specific training example of a four wheeler. So I'm acquiring the knowledge, or I'm learning the knowledge. That concept we generally call it as the general concept it is. And this is just to this the real world example what we have given. It is just to you are learning this one, or you are studying this one in order to score more in the examination. And each such concept can be viewed as describing some subset of objects or events defined over a large set. Each of the concepts can be viewed as it is viewed as a subset of objects or elements or the events defined over a larger set. These are small objects that we are seeing from a given larger set. Let us take an example for example, car is an example, right? It's a subset of all the four wheelers available in the market, right? You have the bus, you have the car, you have something like you have the lorries, and four wheelers you have it. And among all these things we are choosing the car as my example, which is drawn from a larger set, which is drawn from a larger set. Okay. Alternatively, each concept can be thought of as a boolean value function defined over this larger set. Okay, each concept can be thought of as boolean value function defined over this larger set. Boolean value function in the sense that whether you have chosen that particular object or event or not. Okay, if you have chosen that particular object or event, we make it as one, otherwise it will be set to 0. That's why each concept what you're learning, it should be in the form of a boolean value. Let us take for example, you have something called as car, bus, and lorry, you have it. And if you have chosen the car, it will be made as a 1, and the rest of the car, bus, and the lorry has been set to 0, 0, stating that lorry and bus has not been chosen, right? So, and this is how the concept learning works. Alternatively, each concept can be thought of as like a boolean valid function that we have seen it, right? 1, 0, 0, 1 in the sense car I have chosen it, and I have not chosen bus and lorry, right? So out among the four wheelers. And the concept learning a boolean valid function from training examples of its input and the output. This is right. You are inferring a boolean valued function, that is finally, or you are concluding from a boolean valued function from training examples of the training examples of its input and output. You are inferring a boolean valued function from your both input as well as the output. And such boolean valued function we call it as the concept learning. Okay, to state it in a simple words, concept learning is something like you are setting, or you are choosing one object or one or more object from a given larger set, right? And this is chosen, the chosen object has been defined using a boolean subset or a boolean value function. And this whole process we call it as the concept learning. Okay. And let us take for example here, there are simply 6 tasks I have it, right? We have something called as a 6 task. That is, we have a sky, air temperature, humidity. Sorry, 6 tasks I had: humidity, wind, and water, and the forecast. Okay, I have set a task here. Sky. It's all about weather here. Weather, how the weather looks like. Okay, if it is weather, weather is sky, air temperature, and the humidity of the weather, in the weather, wind and water, right? Whether it is too much warm or cool or not. And the forecast, we're just changing whether the weather is going to change or not. Under what circumstances you have to play the game, under what circumstances you are supposed to play the game, that is given as a enjoy sports. There are four instances here. There are four instances we have given it. Let us look at the four instances in detail here. If the sky is sunny and air temperature is warm and the humidity is normal and wind is strong and water is warm and the forecast is same. That means if the entire weather is a sunny weather, warm, normal, and the strong and the warm, and the weather is not going to change under such circumstances, you are going to play the game. That's why enjoy sports has been set to yes, indicating that this particular input has been chosen or this learning experience has been chosen. If the sky is sunny, no issues, we are going to play the game. That's why enjoy sports has been set to yes. Look at the second example here. Sunny, warm, high, strong, warm, and same. Right? If the sky is sunny and air temperature is warm and the humidity is high, no issues, and the wind is strong and water is warm and forecast is same, still we are going to play the game. Even though humidity is high, you look at the values here. Early there is a change in the humidity values. Humidity is high, still we go and play the game. That's why we just set the enjoy sports as yes. We are setting the enjoy sports as yes. And similarly for sky, if the sky is rainy, right, air temperature is cold and humidity is high, wind is strong, water is warm, and forecast is going to change in the next couple of minutes or a couple of hours, right? We are not going to play the game. We are not going to play the game. That's the time. The enjoy sports has been set to no, stating that if this condition, if this is my input, then we are not going to play the game. And look at the values here. If it is sunny and sunny, if the sky is sunny, you are going to play the game. And if it is rainy, doesn't matter what value you have it for the other five uh, instances or the task, what you call it as, or the instances, that is cold, high, strong, and warm, and change. It doesn't matter. You're not going to change the value, or you're not going to play the game. That's why enjoy sports has been set to no. So only this value is going to determine whether you are going to play the game or not. So okay, if it is raining, if it is rainy, then you are not going to enjoy the sports. That's why it doesn't matter what value all other value five will carry it. So now it becomes no. Similarly, for if the sky is sunny, it doesn't matter. Sky is sunny and air temperature is warm, humidity is high, wind is strong, and water is cold, and forecast is going to change it. Then subsequently we are going to create the or we are going to enjoy the sports. So this is how this is how you are going to play the game. So we'll collect the information about all these six parameters every day. We are collecting the parameters of these six one every day, and we are predicting whether you are going to play today or not. You are going to play today or not. If it is sunny, warm, normal, strong, warm, and sing, you are going to play it. If it is sunny, warm, high, the humidity is high, wind is strong, and water is warm, and the forecast is same, then also you are going to enjoy the game. And if it is sunny, uh, so sky is sunny, air temperature is warm, humidity is high, wind is strong, water is cool, and forecast is going to change, then also you are going to change it. Okay, but if the weather is something given as if the sky is raining and air temperature is cold and humidity is high and wind is strong and water is warm and forecast is change, it is going to change, then under such inputs we are not going to play the game, or we are not going to enjoy the sports. So this set of example bases, which each represented by a set of attributes. These are all the attributes of what we have it. So and we have to decide on which particular day you are going to play the sports. And the attribute enjoy sports indicate whether or not a person enjoys his favorite water sports on that particular day or not. This enjoy sports attribute, the attribute enjoy sports states whether you are going to play the water sports on the particular day or not. Out of these four inputs, uh, 3 has marked with the S means that you are going to play the water sports for 3 days, whereas for no indicates that you are not going to play the game for that particular day. So the task is to learn to predict the value of enjoy sports for an arbitrary day based on the value of its other attributes. The basic task. This is my input. This is my input. Okay, and we have stored it in my database, right? And I have all the enjoy sports value here, and I have to decide, or I have to predict the value of enjoy sports for an arbitrary day in the sense any given day, right? For any given day I have to decide whether you are going to enjoy sports or not, whether you are going to enjoy the sports or not. Okay, that is what the things here. The task is to learn to predict the value of enjoy sport for an arbitrary day based on the value of its other attributes. Okay, and what hypothesis representation is provided to the learner. So what is the hypothesis representation? That is, we are going to learn, or we are going to construct the hypothesis, right? Hypothesis is nothing but it is an what do you call it as, it's a representation where you are just giving an idea, you are giving the formula of selecting a particular attribute, or you're giving the formula to select a particular data. Let us consider a simple representation in which each hypothesis consists of a conjunction of constraints and the instance attributes. Let us consider, for example, a simple representation, right? How to develop the hypothesis. The Let each hypothesis be a vector of 6 constraints, right? It can contains 6 constraints here, and specifying the values of 6 attributes, that is sky and air temperature, humidity, wind, water, and forecast. These are the 6 specifying values that is going to be included in the hypothesis. And there are 4 attributes, right? So how the attributes will be given with respect to these 6 values, right? And if a particular attribute is chosen, right, we have to uh, give the name of the value. And if any value is acceptable, that value is that is marked with the question mark symbol. If none of the value is acceptable, no value is acceptable for the hypothesis, then we are making it this symbol, right? So and not symbol, right? So you're not selecting any of them. Now none of the values is acceptable, so these are the 3 values where uh, 3 values you can include it in a hypothesis. Indicate by a question mark that any value is acceptable for this particular attribute, right? Any value is acceptable for this particular what you call it as attribute. Specifying a single required value for the attribute, that is, you can specify a single required value for the given attribute. Indicate by a not that has no value, that is no value is acceptable. Now it doesn't matter which value, you supply it or which value you see it, doesn't matter. That particular hypothesis is not going to accept any of the values. It's okay. And this is when you give the hypothesis with a question mark symbol, we call it as a general hypothesis. It is, we call it as a generalized hypothesis. When you give this one with a not symbol, means that more specific hypothesis, right? We are giving it with a more specific hypothesis. Okay, this is how you can specify the or construct the hypothesis. That is, it might have any of these three values. One is the question mark, second one with a single value, required value, or it can have the not symbol as well. So now, for instance, X specifies all the constraints of hypothesis H, then H classifies X as a positive value. If the input satisfies all the constraints, what is that X? X is nothing but these values. This is 1X, this is second X, and this is third X, and this is fourth X. If any of these one satisfies the or meets the condition of the hypothesis, then that will be marked with the 1. That is, that particular instance or that particular instance is acceptable. That particular instance is acceptable. So that is what they have given it. If some instance X satisfies all the constraints are hypothesis H, then H classifies as X as a positive example. It classifies as X as a positive example. It is why it is a positive example. It means all the criteria of the hypothesis. The hypothesis that person enjoys his foods only on cold days with high humidity is represented by the expression or the hypothesis given as that is, a person who is going to enjoy his sports on any given day, if it is a cold and with a high humidity, doesn't matter. So that is given with the hypothesis called as, so question mark, cold, the weather, the where cold, and the humidity must be high. And look at these values, question mark, question mark, question mark, and question mark. Means that these values these attributes has no importance here. If it is cold and humidity is high, doesn't matter what the sky is, what the weather is, whether water is not, whether the weather is going to change or not, doesn't matter. I am going to play the game. I'm going to play the game. Are you getting? There are 6 attributes here. The first attribute, sky. Second one is what? Second one is air temperature, humidity, wind, water, and forecast. Right? This is air temperature. So sky, and air temperature is cold, and humidity is high. Right? Wind can be anything, whether it is anything, any wind here, and water, either it can be cold or warm, or forecast, either it can change or same. And similarly with respect to sky, it can be cloudy or it can be sunny, right? Doesn't matter, right? Anything, if these 4 values has no importance under such things, if the weather is cold and if the air temperature is cold and humidity is high, I'll go and play the game. I'll go and play the game, even if it is raining, even if it is raining. In such a case, what I will do is that we are choosing that particular inputs. The most general hypothesis that every day is a positive example is represented by question. All of them are question marks. That is, you are going to choose, or you are going to play the game every day. You are going to play the game every day. Why it is? So doesn't matter whether it is sunny or rainy, doesn't matter if it is cold or warm, it doesn't matter if it is humidity is high or low, or doesn't matter whether the wind is less or more, water is warm or cold, or the weather is going to change or not, doesn't matter. We are going to play the game. We are going to play the game. In other words, every day you treat it as a positive example. Every day is treated as a positive example. In other words, where you can play the game every day. The most specific possible hypothesis. I have told you one example in the last slides. We have told it. If it is contains question mark, indicates that it is a general hypothesis. It's a general hypothesis. If it contains not symbol, means that it is a specific example or a more specific hypothesis or the specific hypothesis we call it as. So this is not, no, doesn't matter, right? Doesn't matter what whether you have it, we are not going to play the game. The meaning of this entire hypothesis states that doesn't matter whatever the whether it is, I am not going to play the game, right? So that is what the most specific possible hypothesis, that no is the positive example, that is all the days are negative examples. In other words, we are not going to play the game. So either it is Sunday or Monday or any arbitrary day or any random day, doesn't matter, you are not going to play the game. But in this case, we are playing every day, that is every day is a positive example. Every day is the positive example, whereas this one is a every day is a negative example, right? That is no day is a positive example. And how to specify the hypothesis, right? In a hypothesis, how to specify it? The set of items by which the concept is defined is called the set of instances. uh, that is the set of instances where which the concept is designed is called as the set of instances. We use in set of items, from that one we have built or we have developed the set of instances. We generally call it as the sorry we have developed the concept we have defined the concept, and such examples we call it as a set of instances, which should denote it by x. Which should denote it by x indicates it is the collection of all the items. The collection of all the items. Let us go back to the previous example. 1, 2, 3, 4. These are all the four examples. 1, 2, 3, 4. That is, this is one item, second item, four item, third item, and the fourth item. And all these four items are collectively determines, or using this one we are representing or we are defining the concept. And such items or the set of items we generally call it as a set of instances, right? So which is denoted with a x, that is capital X. But whereas a small x indicates that it is one instance or one item of that set, one item of that instances, right? We are remove or we take out one instance from that x, that is the capital X. We represent it here with a small x, means that it is a subset of the given set. For example, x is a set of all possible days, each represented by the attributes sky, air temperature, humidity, wind, water, and forecast. So, okay, so x is possible days, that is set of all the possible days. That is day 1, day 2, day 3, day 4. We have represented all the attributes in that. We have represented all the attributes in that. The concept or the function to be learned is called the target concept. That is what function you are choosing it, or what function you are learning it is called as the target function, which is denoted by C. Okay, and C can be any boolean valued function, right? Defined over the instances x. So it can be any boolean value, a valid function that is defined over the instances x. Okay, and C colon x is chosen, or if it is chosen it is 0, otherwise it is 1. If it is chosen it is 1, otherwise it is 0. In other words, an item from a set, if an item from the set is chosen, then x is 1, otherwise it is 0, means that we have not chosen the things. So let us go back here, go back to the previous line here, this one. So if the sunny, warm, normal, strong, warm, and same, so then what I am doing is that it is set to S means that we are choosing that particular day. S in the sense that we have chosen it. That's why x equal to 1. X equal to 1. And in the second example, x is also equal to 1. In the third example, it is x equal to 0 because we have not chosen this particular day. But whereas for this one, it is x is all again equal to 1 because we have chosen this particular day. Well, for these attributes, we have chosen this particular, like we can play the game. That's why enjoy sports can be set to S, which is nothing but x equal to 1, means that we have chosen this particular attributes. So let us try to understand this one. That is, for this hypothesis, are you getting the point? For this hypothesis, that is question mark, cold and high, colon, sorry, question mark, and question mark. And what are the instances or the items we are going to choose it? Can anyone tell me? Can anyone tell me? Yes? My hypothesis states that my hypothesis is something like question mark, cold and high, question mark, and question mark. Right? And what is the value of this one? Or what is the value of each attributes? Can anyone tell me? Yes? Sushma? 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 Sushma RK? Madhu G? Madhu? Madhu G? Madhu G? Anjaney? Anjaneya?
Data insufficient, sir.
Data insufficient. Why the data is insufficient? We have given the complete table, right? We have given the complete table. With this, with a given hypothesis, on which day you are going to play the game? Anusha? Anusha MP? Anusha? Yes, are you there? Kumar? Kumar CD? Kumar CD? Prajwal? Prajwal Gowda? Prajwal Gowda? Nazmin? Nazmin?
Yes, sir.
So what is the like we using that hypothesis? Using that hypothesis on which day you are going to play the game here? Using
Sunday.
sets on which particular day you are going to play the game?
On Sunny.
Pardon? On which day
When
you are
it is
going to play the game?
when it is sunny on
Pardon? Amrita ji? Amrita, Amrita G. Yes, Amrita G. Ashwini,
Rainy season.
pardon?
Rainy, sir.
Rainy. Okay, why it is rainy? Why you have chosen only that set? Why you have say chosen only that item? Yeah, why not the other three items? Huh? Divya, Dipesh,
Insufficient of
pardon?
getting. Insufficient
Insufficient.
data.
Why it is insufficient data? You have sufficient data here, right? Four items you have it, and you have the hypothesis, and you just choose the particular item, right? Whatever the Ashwini has told, it is correct because we are just looking at the only these two values. If it is cold and high, humidity is high. If the air temperature is cold and humidity is high, doesn't matter what value you have for the other four attributes, right? We are going to play the game, right? So here air temperature is cold and humidity is high. So that's why I am going to play the sports on this particular day. Look at the other three items. So air temperature is warm, so we are not going to play the game. Air temperature is warm, again we are not going to play the game. And here air temperature is warm, so we are not going to play the game. So humidity normal, we are not going to play the game. But the humidity is high, humidity is high, but the air temperature is, since the air temperature is warm, we are not going to play the game. Are you getting? Humidity is high, no issues. Humidity is high, but the air temperature is warm. So that's why we're not going to play the game on that item. Oh, sorry, on that day. So similarly for the fourth item, so humidity is high, so that is fine. But whereas the air temperature is warm, so I'm not going to play this game on this particular day. So only day where when I can play the game is the third item, that is sky is raining, air temperature is cold, humidity is high, wind is strong, water is warm, and forecast is changed. Then only I can play the game. So that's why it becomes one, and all other becomes zero zero. Or in other words, this is becomes no, this is no, this is yes, this is no, something like that, right? That is how you can see here. That is valid function defined over the instances x. Se colon x derived 0 or 1. If it is chosen, it will be marked as 1 or yes. Otherwise it is given as 0 or no. Example: the target concept corresponds to the value of the attribute enjoy sports if x of c of x equal to 1, if enjoy sports is equal to 1 yes, or if c of x equal to 0 if the enjoy sports is no. So okay, so based on the given hypothesis, we are setting the enjoy sports equal to either equal to s or no. Okay, if c of x has been chosen, if that particular item has been chosen from the set of instances, we make it as 1. That's why enjoy sports becomes 1 s. If the set item has not been chosen, So it means that it is equal to 0. That's why enjoy sports become no. Okay, so this is how you can design the, or you can construct the fix. Instances for which CFX equal to are called positive examples. So for we call it as the, they are called as the positive examples or the members of the target concept. With this example, so how many positive examples you have for this particular hypothesis? How many positive examples you have for that particular hypothesis? Yes? Sneha? Sneha PO? Purnima? Purnima? Jyoti?
Yes, sir.
How many
4, sir.
positive examples you have?
4, sir.
4 positive examples have it for this given hypothesis. For the given hypothesis, this is my hypothesis. For this given hypothesis, how many positive examples you have for this table?
4, sir.
4 positive examples you have it. Yes.
Yes, sir.
Nachket?
Yes, sir.
4 positive examples you have it.
No, sir. Only one, sir.
Only one.
That is rainy.
Yeah.
Rainy, sir.
Rainy, cold, high, strong, warm, and change. Only on this particular day you are
Yes.
going to play the game. That's why enjoy sports is X. So because a temperature is cold and humidity is high, that's why I have chosen only this item, right? Only this item. That's why the number of positive examples are only one. Number of positive examples are only one. Is it right? That's what. Instances for which CFX equal to 0 are called as the negative examples or non-members of the target concept. How many negative examples you have it? How many negative examples you have it with a given example? How many negative examples you have? Yes?
Sir.
Pardon? 3.
Sir.
Why it is 3? These 3 items are not going to meet the hypothesis. Right? They are not according to the hypothesis. That's why they will be treated as a, what do you call it, as the negative examples, or also called as the non-members of the target concept. They are called as the non-members of the target functions. If they had chosen the CFX becomes 1, they are called as the members of the target function concept. If the instance is not being chosen or it is called negative, then they are called as the non-members of the target concept. The ordered pair, that is x comma CFX, to describe the training examples consisting of x and its target concept value CFX. It's a combination of these two. That is x. X is nothing but the item and whether it has been chosen or not. So this combination, this pair, we call it as the target concept value. Sorry, it is the ordered pair here, right? So x, it's nothing but the item and whether you have chosen it or not. So that makes one pair, right? So and D to denote the set of available training examples. D is nothing but the total number of available training examples you have it. So that is given as a D. The symbol H is to denote set of all possible hypotheses that the learner may consider regarding the identity of the target concept. Here comes one more term called as a capital H. Capital H in the sense it is all the possible hypotheses. Okay, so we have designed only one hypothesis here. We have one hypothesis, two hypotheses, and three hypotheses. This is H1, H2, and H3. and the collection of all these three hypotheses is considered as a capital H. So it is placed under capital H. So that's the symbol H denotes all the possible hypotheses that and that the learner may consider regarding the identity of the target concept. Okay, it is just to use to regarding the identity of the target function. Each hypothesis H, that is where we are picking one hypothesis H, that is small h, from the available or all possible hypotheses capital H, represent a Boolean value function defined over x, right? You will take one hypothesis from H, so and we are deciding which item has been chosen. So whether you are going to choose that particular instance or not. If you have chosen the instances, it will be marked as 1, otherwise it is set to 0, right? So that is a Boolean value function. Now a Boolean value function defined over x colon x derives 0 or 1. The goal of the learner is to find a hypothesis H such that h of x equal to c of x for all x in capital. And let us look at the algorithm with respect to the enjoy sports. What happens or how to write the algorithms. So given values. What are the values that is given by the things? Instances. Instances of x possible days, each described by the attributes. So we are just accepting the inputs. This is my inputs called as x, and it accepts 6 different attributes or 6 different values for the given attributes. So attributes name are sky, air temperature, humidity, wind, water, and the forecast. These are the 6 values, these are the 6 attributes, alright. And for these 6 attributes, we are accepting the values for each day. And the possible value for each attribute is, so for sky, it is a sunny or a cloudy or rainy. Only these 3 values are acceptable, right? On a given day, either the sky can be sunny, sky can be cloudy, or sky can be rainy as well. Whereas the air temperature attribute can have 2 values, so warm or the cold. So either a particular day or an arbitrary day can be warm or it can be cold as well. So similarly for attributes, humidity, it has 2 values. It can have 2 values. Either the value can be normal or it can be high as well. And similarly, the wind attribute can have 2 values, strong and weak. It can have 2 values called as strong and weak. And the water attribute contains the 2 values, warm and the cool. And the forecast, similarly, we can have 2 values, the same and the change. Same and the change. So these are the 6 attributes, right? And each attributes having different values here. Each one of them is having different values, and it is going to be evaluated. Look at this example here. On a particular day, let us look at the attributes here. Sky is my attribute, right? So on any given day, the sky can be either sunny or rainy. No other values are allowed here. No other value is allowed. Similarly, for air temperature, the value can be either what we call it as warm or cold. Look at this one. Air temperature, either it can be warm or cold it is. Humidity, normal or high. And similarly, wind may be strong or weak. Wind may be strong or in this case, all of them are strong. Okay. And water, it can be a cool one or the warmer one. And similarly for forecast, it can be same or change. It's same or it's going to change it. And this is the first given input values, and followed by we have to build the hypothesis. We have to build the hypothesis called as H. Each hypothesis is described by a conjunction of constraints on the attributes sky, air temperature, humidity, wind, water, and the forecast. The constraints may be question mark, or it can be what you call it as not, or it can be any specific value. In the last example, we have seen it, an hypothesis can have any of these constraints. The first constraint can be a question mark, that is any value is acceptable, and no value is acceptable, that is denoted by no, and a specific value is specified by specifying the value of that particular attribute. So this is the second hypothesis or the second value that is given by the things, and we have to beat the target concept. We have to beat the target concept, that is enjoy sports or called as a C. So whether that particular instance is zero or not, or whether it is acceptable or not. Okay, and if the instance if it is going to meet the hypothesis criteria, it will be set to zero. Sorry, it is not, it is set to 1, otherwise it is set to 0. It's set to 0. And the next one is the target examples, D, that is a positive and negative examples of the target functions. Okay, we have to look at the target positive and the negative examples of the target function, whether that particular example can be included in a training or not. Okay, these are the some given values for the the concept learning. First one is the instances, second one is the hypothesis, third one is the target concept, and fourth one is a training example. And what you are going to determine using these values. So you are going to determine a hypothesis h in h such that h of x equal to c of x for all x in x. That is, you are going to select an hypothesis that is going to accept one instance variable, or the one instance of the all other given, or the all the given instances. So that is how, that is a hypothesis h in h such that h of x equal to c of x for all x in x it is. That is, you are going to accept the one or more instances which is going to meet the hypothesis criteria, okay, from the given instance set it is. This is how your the concept learning task actually works for the given enjoy sports game it is. Okay, enjoy sports, right? And next one is the inductive learning hypothesis. Any hypothesis found to approximate the target function well over a sufficiently large set of training examples will also approximate the target function well over other unobserved examples. So inductive learning hypothesis states that if the target example, or if the hypothesis is going to approximate the target function for a sufficiently large training examples, then obviously that hypothesis is going to approximate the target functions which are well over the unobserved examples. So what do you mean by that? You look at the example here. I have I'll take one example here, that is question mark, code, high, and these three. So now which one will be accepted here? Which training instances will be accepted? It must be cold and high. So only this value will be get accepted. Only this value will be get accepted, or this instance will be get accepted. For this one it is positive. Okay, and if your hypothesis works for this input, this is a specified inputs, then obviously your hypothesis is going to work for the unobserved instances as well. Okay, whatever this is my observed instances, right? It is, or also called as the sample training examples. And if your hypothesis is going to work for a set of training examples, obviously it is going to work for the unobserved or unidentified training examples as well. So that is what the meaning of the inductive learning hypothesis. Any hypothesis found to approximate the target function well over a sufficiently large set of training examples will also approximate the target function well over the other unobserved examples. If your hypothesis works for a set of a sufficiently large set of training examples, it will obviously work for the other unobserved examples as well, other unobserved examples as well. And you're just using the concept learning as a form of the search as well. What is that concept learning is all about? Let us look at that. A concept learning can be viewed as a task of searching through a large space of hypotheses implicitly defined by the hypothesis representations. You're just concept learning can be viewed as task of searching through a large space of hypotheses implicitly defined by the hypothesis representation. We have very large number of hypotheses, and out of these available hypotheses, I am looking for one hypothesis or more hypotheses which are going to meet the hypothesis representations. The goal of this search is to find the hypothesis that best fits the training examples. You may have hundreds or you may have few hypothesis sets, and out of these hypothesis sets, only few hypotheses or one or two hypotheses is going to best fits the training examples. And to search for this one, we are using the concept learning. For example, the instances X and the hypothesis H in Enjoy Sports Learning task, the attribute sky has three possible values. Either it has three possible values: air temperature, humidity, wind, and water can have or forecast can have two possible values. The instance space X contains exactly what it can have 3 into 2 into 2 into 2 into 2 into 2. That is 96 distinct instances you can have it. You can have 96 distinct instances you have it. And for this 96 distinct instances, I can have something called as 5120 distinct hypotheses. I can have 5120 different syntaxes or they have distinct hypotheses. Why it is 5 here? Why it is 5? Can anyone tell me? Why it is 4? Why it is 4? And so on. Why it is 4? Yes? Why it is 5? Why it is 5? Bhagya Chauhan. Bhagya Chauhan. Guddappa. Guddappa. Yes. Nikita. Nikita Bandari. Shivalila. Shivalila.
Sir, the attributes of the sky has
Pardon?
three positive values, sir.
Why it is 5?
The sky has a three attributes, sir. That is air temperature, humidity,
Pardon?
wind, water.
Little louder.
The sky has a three attributes, sir. That is the air temperature, humidity, wind, water, and forest. So it is the 5 values, sir.
No. What I am telling is that it is 5. Why it is 5? Hypothesis can contain 5 different values for sky. What are those 5 values? What are those 5 values?
Attributes.
Pardon? That's what I'm
Attributes.
telling you. For this attribute, the sky is an attribute, right? And for this sky attribute, it can have 5 values. That is mean. That is the meaning. So what are those 5 values? Nazmin, Nazmin, Vincent, Vincent Paul, yes, Vincent Paul,
Sir, because there are 5 synthetically distinct hypotheses,
pardon?
sir. There are 5 synthetic distinct hypotheses are there, no, sir?
What are those 5 distinct attribute values?
Mm. 1 plus 4,
Pardon?
3 and
Okay,
sir,
a sky can have 3 values actually. So that is given in the first one, that is the distinct instances you can create it. 3 value for the sky, 2 value for the all other attributes, that is air temperature, humidity, wind, water and the forecast. All of them are can have in the things. And each attribute can have 2 more values. Implicitly, each attribute can have 2 more values. So let us take for example, sky can have 3 values, right? 3 possible values. It can have the sky, it can have the cloudy, it can, sorry, sky can be sunny, or it can be cloudy, or it can be rainy, right? 3 possible value you can have it. And apart from these 3 values, there are 2 more implicit values. One is a question mark and second one is the not. Okay, that's why it has become 5 here. That's why it has become 5. And similarly, it holds good for all other 5 attributes as well. For a temperature, the actual values are 2. Is it right? But the number of hypothesis attributes that you can give is 4. So two, the values of the heat temperature, and 2 implicit variables, that is implicit values called as a question mark and the not. In keeping all these things, I can design or I can construct 5120 syntactically distinct hypotheses within H. Let me brief you. Let me show you how it works. So for sunny, I'll just sorry, for sky attribute, I can write it as. All of you can hear me clearly. All of you, is there any network issue on your side, or is there any network issue from my side? Someone is pinging here. Someone is pinging that is there is some problem here. Okay. So I think Mushtaq, Mushtaq,
Yes, sir. Sir, sometimes his voice is breaking,
Mushtaq, there is some problem on your side. Just check it out, because all other participants are saying that they don't have any problem in listening to me. Is it right, Mushtaq? Okay, let me explain you. For sky, it can have 5 values, right? Let us see here. It can be sunny and all other five values. Let us see here. Let us see. Is it right? That is one hypothesis. And like this, what I can have is just do it. I can, for this kind, let me write it here. For the first option, it may be sunny, is it right? Followed by, right? So something like this, right? That is one value. It can be cloudy. It can be cloudy and followed by these things. Don't, right? And for the third one, it can be rainy and followed by this one, or it can be anything. Is it right? It can be anything followed by, and it can be, the first attribute can be nothing. Is it right? It can be nothing, right? I'll mark it as 0 and 0 and 0, and it can be followed by something else. Then how many hypotheses were constructed using only 5 values of the sky attribute? How many hypotheses? 5 hypotheses you have designed it, right? Using only 5 values. Apart from the available 3 values, that is sunny, cloudy and rainy, there are 2 more implicit values called as question mark and the not. That is what you have to look into. Okay, so we're using this one. I can have for sky, it is 5 possible hypotheses. For air temperature, it is 4, 4, 4, 4, and 4. So there are 5,120 syntactically distinct hypotheses. We can design it. So out of these 5,120 syntactically distinct hypotheses, we have to pick only few hypotheses which are going to meet all the instances. Every hypothesis containing one or more not symbols represent the empty set of instances. That is, it classifies every instance as negative. It classifies every this one as negative. That's why we'll omit that one or we'll remove that one. That's why with that one I can have only 973 distinct syntactically distinct hypotheses. We can classify, or we are going to have only 973 distinctly syntactically distinct hypotheses. And general to specific ordering of the hypothesis. How to make use of the, or how to go from general to specific ordering of the hypothesis. So consider the 2 hypotheses, H1 and H2. So I have a more generic hypothesis. Both of them are more generic hypothesis. Why it is called as more generic hypothesis? Look at this one. Only first attribute is more specific, and the remaining 2 are generic one or the general attributes, and this is specific one, and these 2 are generic one or the general one. So we write S2, that is hypothesis 2. The first attribute is generic and the next 5 attributes are very specific one, very generic one, whereas sunny is more specific one. Consider the sets of instances that are classified positive by H1 and by H2. So okay, let us look at the what are the things, what are the instances that are classified positive for H1 and for H2. S2 imposes fewer restrictions on the instances. That's why it is called as general instances, or the general hypothesis we call it as. It classifies as more instances as positive. It classifies as more instances as positive. So any instance classified positive by H1 will also be classified positive by H2 as well. Okay, if H1 is going to make an instance as positive, obviously H2 is going to make the same instance as positive, because look at the attribute here. Attribute can be anything, right? It can be anything. So even it can be strong as well. The strong is a part of anything, right? That's why if an instance is identified as positive by the H1, that is the hypothesis 1, then H2 is obviously going to make them as positive as well. So, okay, H2 imposes fewer restrictions or the fewer constraints on the instance. So that's why it is a generic hypothesis what you have it. It classifies as more instances as positive. Okay, so any instance classified positive by H1 will also be classified positive by H2 as well, not vice versa. Not vice versa. But if the H1 has classified the instance as positive, obviously H2 is going to make them as positive. Therefore, H2 is more general than H1. H2 is more general than H1, whereas H1 is more specific than H2. H1 is more specific than H2. So, given the hypothesis H of J and H of K, Hj is more general than or equal to Hk if and only if any instance that satisfies Hk also satisfies Hi. So, okay, so or Hj, sorry, it is. If I say that H and K, Hk and Hj and Hk, Hj is more general than or equal to H of K if and only if, what I say that, any instance that satisfies Hk also satisfies, make it as Hj it is Hj. If Hj is going to satisfy some instances, or if it is going to treat an instance as a positive example, then obviously Hj is also going to treat them as a positive example. Why? It is because Hj is more general, or it can be equal to Hk. That's fine. Whatever the instances identified as positive by Hk can also be identified as positive by Hj as well. So that is how the definition works for the general to specific ordering here. Definition: let Hj and Hj be Boolean valued functions defined over X. Then Hj is more general than or equal to H of K. Written Hj is more greater than or equal to H of K if and only if for all X belongs to X, H of X equal to 1, then Hj of X is also set to 1. Which means that if an positive example is set by H of K, if an instance is set as positive example by H of K hypothesis, then obviously the same instance can be set as positive example by Hj, which is nothing but an hypothesis. So this is what the general definition of the general to specific ordering of the hypothesis. Let me repeat it once again. Given, let H of J and Hk be Boolean valued functions defined over X. It is nothing but a set of all the instances. Then Hj is more general than or equal to H of K, written as Hj is greater than or equal to Hk if and only if for all X which belongs to or which is a subset of X, right? If Hk has identified a particular instance as positive example, it is given as 1 here, then The HI, that is, HJ, which is an hypothesis, also recognizes the same instance as positive example. It's going to identify the same instance as a positive example. So look at the example here. We have instances, that is, all these instances we have it, x1, x2, and all the things, right? X1 is equal to sunny, warm, high, strong, cool, and same. H2 is sunny, warm, high, light, warm, and the same. What that hypothesis I have it, H1 is sunny, can be anything, strong, and these two, and H2 can be H2 hypothesis. H2 is going to identify it as sunny followed by 5 things, and H3 sunny, 3 question marks or 2 general values, and followed by cool and things. So using this one, we have to have some try to understand how this actually works. H1, what are the instances that is marked as in positive by H1? That is sunny, then sunny is there, and these two values can be anything, strong, and then these two values can be anything. That is, H1 is going to make X1 as positive. That is fine. And as far as this one, that is sunny, it is there, and these two values, and this is not right. Okay, that's why H1 is going to make X1 as positive values or a positive instance, whereas S2, it is sunny, then 5 question marks. That is, with that one, both of them, that is X1 and X2, X1 and S2, are nothing but the positive example for hypothesis H2. They are nothing but the hypothesis H2. Is it right? And similarly for H3, sunny, then followed by the 3 question marks, the cool and the question mark, means that it is going to accept only the first instance with that one, but because it is sunny and followed by the cool. So with this one, H2 seems to be more generic one. H2 seems to be more generic one compared to H1 and H3. So H1 and H3 are more specific one, whereas H2 is treated as a more generic one or the general hypothesis. That's why whatever the instances that is marked as positive by H1 as well as H3 can be marked as positive by H3 as well. That is how your the entire instances work. We have X1 and X2 here, and H2 is what? It's going to accept both of them. That is, H2 is it's going to accept all the 2 instances. It's going to accept all the 2 instances, whereas H1 is going to accept only X1, and S3 is also going to accept only X1 as well. That's why X2 is more generic or the general hypothesis than H1 and H3. So that is what. In the figure, the box on the left represents the set X of all the instances. The box on the right is a set of all the hypotheses. This is a set of all the hypotheses. And on the on the left side, we have set of all the instances. Each hypothesis corresponds to some subject of X, the subset of instances that is classified as positive. So each hypothesis corresponds to some set of X, the subset of instances that it classifies as positive one. The arrows connecting hypotheses represent the more general than relations. Okay, so more general than relations. So we are just connecting them, stating that these instances are marked as a positive by that particular hypothesis, with the arrow pointing towards the less general hypothesis. Even you can see here, this is more general hypothesis. What we have it, we have one simple general hypothesis. It's going towards this one, means that H2 is more generic one compared to H1 and H3. They are more specific. So when you go upward in this direction, so you are just going to have more specific hypothesis. So that's why you can see it here. So we can have we can have more specific hypothesis as you go towards the end, and if you come down you will get more general hypothesis. This is more general hypothesis, and if you go upward in the direction, yeah, you will just get the more specific hypothesis. Note the subset of instances characterized by H2 subsumes the subset characterized by H1, hence H2 is more general than H1. Similarly, it holds good for H3 as well, because H3 is going to have more specific attributes, whereas H1 is having more general attributes. That's why H2 is more general than the H1, as well as H2A is more general than the